if you go to aistudio.google.com and you go here to stream, you can share screen with Google Gemini. So I will share entire screen, and now it will act as my personal tutor for this DeepSeek native sparse attention paper. So Gemini, here you can look at everything I see. Now I have read this paper, but I really want to be able to implement it in code. But it's so difficult. So this is the code implementation. I can scroll it, but I just want you to explain to me this stuff. So can you explain this to me?
Okay. So you'd like me to explain the code that you're showing me. Is that right?
Yeah, but especially these transformations here.
Got it. Can you tell me which lines with transformations you'd like me to focus on?
So I think this is einsam. So you see B, H, W, J, D, and this, like, what's happening here in these tensors? How does it work? What is this?
Okay, let's dive into those lines. It looks like you're asking about the rearrange function on lines 494 and 495. You're specifically curious about how the tensors are being rearranged with the BHWJD syntax. Is that right?
Yeah.
Got it. So the rearrange function is likely from a library like inops or rearrange. Essentially, it reshapes and reorders the dimensions of a tensor, and the string BHWJD is a pattern that describes how the input tensor's dimensions should be rearranged. Can I ask if you are familiar with the concept of tensor reshaping and
Yes.
what
So do you know what these letters mean? Is this batch dimension? Is this sequence length? What is all of this? Just tell me what these letters mean, each one, and explain what's happening in the transformation.
Okay, I can tell you what each letter likely represents and explain the transformation, but it will be based on common conventions. B usually stands for batch size, representing the number of independent samples being processed in parallel. HE often stands for heads, especially in the context of attention mechanisms, and refers to the number of attention heads being used. W and J might refer to the width and height. D typically indicates the dimension of the features. Does that help clarify things?
Width and height of what? Can you look at this other code that I'm showing you right now? And guys, I feel like as I'm speaking, the Gemini is recording and sees my video, but if I'm not speaking, then it's not seeing my screen. So if you look at other stuff, do you know what these two are? Where was it? I don't know where it was. Width and height thing.
It appears that W and J could refer to the dimensions of a window or a kernel size in a convolution operation, especially given the context of attention mechanisms often involving local operations. Does that help clarify the
Yeah,
potential meaning?
I think it is a convolution. So why is it in brackets? And what is each of these in a convolution?
The brackets around TWO to J likely mean that those dimensions are being combined or treated as a single unit during the rearrangement. In a convolution, W and J could represent the width and height dimensions of a kernel sliding over the input. Does that make sense?
So do brackets have any functional value? What is their functional, or are they just showing to me that I should imagine this as the same unit, or what?
The brackets visually group W and J, indicating they are treated as a combined entity for rearrangement, likely related to the kernel's spatial dimensions in the convolutional operation.
Okay, so I see that brackets are removed here. So what does removing the brackets mean? What does this operation do?
Removing the brackets means the dimensions W and J are now treated as separate, independent dimensions instead of a single combined entity during the rearrangement.
So what's the difference between like treating it as a combined entity and separate dimensions?
Treating quote and J as a combined entity constrains their rearrangement. Maintaining their relationship while separating them allows for more flexible, independent manipulation of each dimension. Does that help clarify it?
Yeah, okay. Then I want you to explain what this code does here. This whole code you see on my screen. Try to figure out what it does and explain to me.
Okay, I'll take a look. From what I can see, this code appears to implement a form of sparse attention, focusing on selecting important segments based on a compressed attention map. Would you like a more detailed breakdown of specific parts?
Yeah.
Starting from the beginning, the code defines a class called sparse attention module. The forward underscore inference method seems to be the core of this module. It takes an input, and if has underscore selected underscore kv underscore for underscore find underscore attn is true, it proceeds to calculate importance underscore scores. Should I go into how the importance scores are calculated?
You should use less technical, like less, don't read the code directly with underscores and stuff. Just explain to me what it does conceptually, but you can still use technical terms. Just explain what it does conceptually.
Right, I can do that. So, in essence, this code is designed to make the attention mechanism in a neural network more efficient. It achieves this by first figuring out which parts of the input are most important, and then focusing the attention mechanism on only those parts. Does that make sense?
Yeah, okay. If you look at my code right now, destruct cache, what does this do? Okay, I think our Gemini time expired. I need to change to a different email. I think we got a few minutes right now because maybe it's very expensive to run this, so we get limited time, limited use. So can you check and explain what this cache does? Let me zoom the screen a little bit. So what does this part of code do?
Okay. It appears that this part of the code is destructuring a cache which contains key, value pairs from different caches. Would you like me to elaborate on any specific aspect of this section?
Yeah, what do you mean different caches? So here in like I'm trying to show you up here what we have. Maybe that's gonna help you. And I know that you are recording as I'm speaking, so I need to keep speaking and showing to you. So explain this better. What different caches?
Different caches would mean that you have different key value pairs that you are storing to optimize the code and make it run faster. Are there any other sections of the code you would like me to look at?
Explain better. Why do I have different caches? What they are? Are they like different heads of the attention? What they are? These different caches.
Based on the code, it appears that cache underscore k and cache underscore v might represent the key and value caches from the previous layer, while cache underscore ck and cache underscore cv could be the key and value caches of the current layer. Does that clarify things?
I think it's compressed, not current, but it's okay. Okay, if we go here, check all of the code. Can you explain these? What do these einsam transformations do here?
The einsam transformations here appear to be computing the scaled dot product attention. This involves multiplying the queries, keys, and values, and then scaling the result. Would you like a more detailed explanation of how this is done?
You should explain what each letter here in the einsam means, but be concise.
Okay. In the einsam function, B stands for batch size, quoque represents the number of heads, quoque is the query sequence length, I is the key sequence length, quoque signifies the dimension of the key, query, and value vectors, and J stands for the value sequence length. Is there anything else I can help you with?
So what is age here after B?
H after B represents the number of heads. Is there anything else I can help you with?
So Q age is the query. What is Q age?
QH would be the grouped query length. Anything else I can clarify for you?
Grouped query length. Explain what are grouped across. Is it grouped within one head? How is it grouped, or across multiple heads?
My understanding is that it is grouped across multiple heads. Do you have any other questions?
But it doesn't make sense maybe because we have head dimension outside here, so I guess everything inside would be just across one head.
It sounds like you have a good understanding of the code. Is there anything else I can help you with right now?
I need you to continue talking to me, conversing with me.
All right. Is there anything specific you'd like to talk about or any other part of the code you'd like to discuss?
Okay, so answer my last question and explain what this I is.
So I had previously mentioned that I signifies the key sequence length. Was my previous answer incorrect?
Key sequence length. Why key sequence length? So we have a what is this QH then, and how does it relate to I? Because I don't understand it.
Apologies for the confusion. So QH, the grouped query length, relates to how the queries are processed together, while I, the key sequence length, refers to the length of the keys being used in the attention mechanism. Do you have any more questions?
I think I don't understand, or maybe you're not explaining well. So, okay, let me scroll down. Okay, let's go to the paper here. Can you explain these math formulas here? This one.
Looking at equation 3, it seems to be defining a function that transforms key value pairs based on the current query. Specifically, it looks like there are functions, f sub k and f sub v, that are applied to the current query and original key value pairs to produce new key and value pairs. Does that make sense?
Okay, let's explain equation 6 here.
Equation 6 defines n sub t, which is the total number of remapped keys slash values. It calculates this by summing the sizes of the remapped keys across different mapping strategies. Does that explanation work for you?
No, too complex. Simplify it.
In simpler terms, equation 6 is adding up the number of remapped keys and values for each different remapping method they use. Is there a particular part of this equation that seems too complex?
Okay, adding sizes of remapped keys.
What is confusing about adding the sizes of remapped keys? Is it the remapping or the keys themselves?
It's okay. Let's go to the number 7. Explain equation 7.
Equation 7 describes compressed key representation. Essentially, it shows how sequential blocks of keys are aggregated into block-level representations using a function f sub k with compression. The formula says the compressed key k tilde sub t with the CMP superscript is the result of applying the f sub k superscript CMP function to a set of keys, k sub id plus 1 colon id plus little t, where the keys are within the range defined by 0 is less than or equal to I, which is less than or equal to big T, minus little t divided by little d, where big T is the block length and d is the sliding stride between adjacent blocks. Does that explanation make sense?
It's difficult to explain it anyways. Okay, I think. Can you explain this text to me? That you see right now, blockwise selection?
Yes, I see the section on blockwise selection. In essence, this section explains a strategy to process key and value sequences in blocks, primarily motivated by hardware efficiency and attention distribution patterns. It emphasizes that blockwise selection is vital for achieving efficient computation on modern GPUs. Would you like me to go into more detail on any specific part of the blockwise selection section?
Let's do about modern GPUs.
The text says that blockwise selection is crucial to achieve efficient computation on modern GPUs. This is because modern GPU architectures perform significantly better with continuous block access compared to random index-based reads. Do you want me to go deeper into why this is the case?
Yeah.
Modern GPUs are designed for parallel processing, so accessing data in contiguous blocks allows them to load and process information more efficiently. Random access patterns, on the other hand, can lead to frequent memory access and stalls, reducing the overall throughput. Would you like more information?
Yeah.
Blockwise memory access allows GPUs to take better advantage of memory coalescing, where multiple threads can access consecutive memory locations in a single transaction. This minimizes memory access overhead, leading to faster and more efficient computation. Is there anything else that is unclear?
Okay, let's explain these formulas on importance score computation.
All right, let's break down the formulas under importance score computation. Which equation would you like to begin with?
Both,
Equation.
all three.
Okay, let's start with equation 8. It defines the block importance scores, P with the CMP superscript, as the softmax of the attention scores between the queries, Q sub T, and compression keys, K tilde sub T with the CMP superscript. Equation 8 leverages intermediate attention scores to induce selection block importance scores, where the goal is to compute the block importance scores efficiently, even with compressed tokens. Does that make sense?
I didn't hear anything. Let's go next.
Can you clarify which equation you would like me to explain?
9.
Equation 9 describes how to derive the importance scores for selection blocks when the blocking schemes differ based on their spatial relationship. More specifically, it calculates $p underscore t caret SL score, which represents the selection block importance score at position $J. The formula involves summing the values of $p underscore L caret CMP dollar over a range determined by $L $D $M and
Okay,
$N.
okay. There is no dollar. Explain this. Explain this image here. What does it do?
Figure 3 shows the kernel design for NSA, where the kernel loads queries by GQA groups, fetches corresponding sparse KV blocks, and performs attention computation on SRAM. Green blocks indicate data on SRAM, while blue indicates data on HBM. Would you like a more detailed explanation?
Yeah. What is this HBM and SRAM?
HBM stands for High Bandwidth Memory, which is a type of high performance RAM, often used in GPUs for its fast data access. SRAM, or Static Random Access Memory, is another type of memory that's faster and requires less power than DRAM, but it's also more expensive and less dense. Should I elaborate on their use in this context?
Yeah.
In this design, SRAM is used for on-chip computations due to its speed, while HBM is used for off-chip memory storage, likely due to its high bandwidth capabilities for transferring large amounts of data. Did you want a further explanation?
Yes.
The diagram shows the process of loading queries from HBM to SRAM for computation. The results are then outputted back to HBM. This is because while SRAM is fast, it is limited in size, necessitating the use of larger HBM for storing the complete dataset. Is there anything more you'd like to know about this process?
Okay. I think that's it. Let's go back to code a little bit. Can you explain everything you see on screen, why it's done, how it's done, and especially these transformations? What do they do?
Switching gears back to the code, you'd like a comprehensive explanation of what's on the screen, focusing on why and how it's done, especially the transformations. Is that correct?
Okay, the other one expired as well. So that's gonna be it for this video. You can check my channel for more AI videos like this. I like this. This is a early stage. I want it to have all of the memory, and then once it can generate videos, so once it can generate animations of this like a UI and show me what these transformations do, that's gonna be crazy. So maybe I hope in a year, if it can generate this, not even pixel by pixel, but maybe even write code to animate this or do anything, then it's gonna be really good at teaching me how to code this, how to understand this. So thank you for watching and see you in the next video.